Good morning, everybody. Thank you, Andrea, for the introduction. Well, today I'm going to show you, a brand new way of attacking passwords and what you can do about it. Especially, it's about tailored machine learning-driven password guessing attacks and its mitigation. A few years ago, probably after watching too much Mr. Robot, I got back to university and decided to do my second master, this time in information security. And the result was this, basically. This is my master thesis. And the title is Machine Learning-Driven Password Lists. And it deals with how you can attack passwords using machine learning, especially human passwords and individual passwords. And also what are ways to mitigate those issues. And first of all, let's talk about the problem of human passwords. We all know there are so many problems with human passwords or with passwords in general, but one aspect is key to my special talk here. Basically, people use password creation schemes when they make up a password. So first of all, there are several types of passwords, like machine random passwords. These are the perfect passwords, completely random, high entropy, and so on. Special character usage, and so on. And then there are human general passwords, like 1, 2, 3, 4, 5, 6. And then there are human individual passwords, which use individual information in their password, like John 1970 exclamation mark. And then, of course, there are human random passwords. These are very rare. People use them like when they randomly type a password and they copy it somewhere in a text file somewhere to save it. They really look like machine random passwords in some cases, but they actually not. But what about correct horse battery staple? Maybe you know that XKCD comic. Actually, this kind of password could be a machine random password if it's randomly chosen by a machine, or it could also be a human individual password. So for instance, if the person selected the word horse because the person likes to ride horses, then it would have some individual entity in there. So what's the basic issue here? The issue is that all these human passwords have a reduced entropy, which means that if an attacker knows the scheme, the password creation scheme, and has some personal data, then he might be able to guess the password or at least narrow it down to a significant bit. And as we can see in password leaks, humans are limited in their creativity. We see that password schemes get reused a lot across several people. So many people have the idea of like adding an exclamation mark at the end. And we can analyze that by those password leaks. And if somebody has come up with such a password scheme, then well, it might be available in these password leaks. So usually when you attack passwords, there are 4 ways to do so. Many times they get combined. The basic approach is a hybrid or rule-based approach. So it's basically using a dictionary and using word mangling rules by some tool. You could also use Markov models or any statistical methodology to use high probability character sequences. Or you could use masks, which reduces those passwords to common structures. And then, of course, there's brute forcing, where I basically try out every combination. And you see, the far more right you go here, the higher the key space, which means in an ideal attack situation, you have the perfect dictionary, so you can stay on the left side, and the ideal dictionary only has 1 entry, and that's the correct password. Of course, this is not the reality, but what we should strive to do is to create the best possible dictionaries for our victims if we want to attack a password. And there is tool support for that. You might know these tools. What's interesting though, PAC, for instance, that's a password analysis tool where you basically feed it with a password list and it generates rules and masks and so on. So there is some kind of statistical analysis already in a high quality possible. If you need dictionaries, then there are several approaches. The most common approaches is just to use a password leak, like the RockUTXT password list, or the exploit in database or password list, or the anti-public combo list, whatever you want to take. So basically, you take some existing password leak and you attack the password. And that's, for instance, here that's the the most common passwords in the rock.txt. Rock.txt is pretty old, by the way. But in some cases, you don't want to attack all the passwords. You want to attack specific victims. And in this case, there are two tools out there. First of all, is Cool, which is a web scraping tool. So you basically point it to a URL of a victim. So for instance, if the victim has a blog, you point it to the blog, and it extracts keywords. And these keywords can be used as a dictionary. So this would be an example here. And then you could also use CUP. CUP is basically asking you as an attacker predefined questions about the victim. So for instance, what's the name of its pet or the year of birth and so on. And then it creates combinations. But there is an inherent problem with this approach. The developer of this tool has to think of password creation schemes. And that's not very flexible because password creation schemes change all the time. And you always have to rely on the developer that those schemes are the ones that the victim will use. I'm going to show you a better way to do that, probably. And first of all, we have to talk about machine-generated text. How is that even possible using machine learning? I used a machine learning model called neural networks. Neural networks is part of machine learning and basically abstracts the human brain. So the human brain consists of several neurons, and these neurons are interconnected to a network. A neuron basically has some inputs, does something with the information, and has some output. And that's interconnected. So you have these input layers, you get information in there, then you have hidden structures in there, hidden layers, which basically save intermediate information, and then you have an output layer that says something about the information. And what neural networks can do for you is that they can analyze huge data sets, like password lists, and they can learn hidden structures, like password creation schemes. And they are also able to reproduce or analyze this new data. That's part of supervised learning, which means that you basically train it on data and also test it on data. Then you generate a model here. Maybe you can read that. You generate a model. A model is nothing else than a file with a lot of numbers in there. And in the end, you use this model to analyze or generate something. There is a specific kind of neural networks called recurrent neural networks, or RNNs. That's basically several neural networks that are able to analyze and generate sequences. And the password is nothing else than a sequence of characters. So for instance, it predicts the next character in a sequence, in a given sequence. And after that, it predicts the next character, and the next, and the next. And then you get a password, for instance. And a password list is also nothing else than a sequence of characters. It's just passwords are separated by a new line character. That's just another character. So this would be our neural network from before. So you have this input, you have this intermediate representation, and then you have an output, and it basically feeds not only into the output as we have in the neural network, it also feeds back into itself, which means that you can chain neural networks. So you have a chain of neural networks, and now it's possible to analyze structures. There's a tool out there called CAR-RNN, written by Andrei Karpathy. And this basically allows you to predict character sequences. So you train it on text and generate text. And you can all install that on your computer, try it out, play with it. There's funny stuff to do with that. So for instance, you could feed it with the works of Shakespeare. So you train it with a lot of Shakespeare text, then you generate new output. And this is actual new output here. And if you read it, it really looks like it was created by Shakespeare in terms of syntax, in terms of words. Of course, on a semantic way, it doesn't make really sense. So there is no coherence in there. But as you can see, sentences start with uppercase letters. They end with dots. They have these typical words in there Shakespeare uses, and so on. And remember, this is character-based. So this is not word-based. If it would be word-based, then we could actually implement semantics. In this case, it's character-based. But it's remarkable what you can do with this tool. You could also feed it with Linux source code, for instance. In this case, this is an actual, I mean, you can't really hardly read it here, but this is actual output, and what you can see here, that's correct syntax, mostly. I don't think it would compile, but it's very interesting though, because you have things like curly braces here. And if you have a curly brace, then the indentation level automatically indents one level. And if the curly braces ends, then here, for instance, if it ends, then the indentation level goes back. And that's all learned by the neural network, which is remarkable. Of course, the code doesn't make any sense because it's character-based. But you could also feed it with a password list, like the rock.utxt. Use the rock.utxt here and generate new password lists, which are like the rock.utxt password list, but not the same. So there are actually new entries in there. So you have typical date structures in there, you have words in there, you have these integers at the end that you see very often, and so on. So why would you do that? I mean, you already have the rock.utxt. Well, if you want to attack passwords and you use the rock.utxt and the password is not on a list, you have to do some statistic methods or some rule-based approaches and so on. And if you need to use brute forcing, then it's better to do something like this. Instead of trying out every possible combination, stick to the ones that are typical for password usage. So this was analyzed by William Mellicher and some folks in 2016. And he basically compared several methods. So he compared Hashcat and John the Ripper with the state-of-the-art rule sets, also probabilistic context-free grammars, Markov models, and neural networks. And what he did is basically what you can see here, here's the guesses, a number of guesses, and here's the percent guessed. I think he used some kind of reference data set. So at any given point, the higher the line, the better, the more passwords were guessed. And in the beginning, you can see that it really doesn't matter which method you take. Probably you're best off with the Hashcat and John the Ripper approaches. But at some point, you see that neural networks have way better guessing performance here. And there's even here where Hashcat and John the Ripper just stop because they don't have any more possible passwords. That's about 10 to the power of 8 or 10 or something like that. At this point, John the Ripper rules are stopping and you can switch to neural networks. But that's just the general approach. Now I'm going to talk about the things I have done, and that's new. Basically, how to attack individual passwords. And why is this relevant? Why individual information is relevant in password? This is some kind of, this is a password list, a sample of the exploit in password list, and I just took a sample here and I marked all the passwords where I think they have some individual context here. So for instance, this person probably likes to drive a 404. This person probably likes to play basketball. What about this person here? Or women, I don't know. Basically, what I want to tell you here is that people use individual information that relates to the person in their password. Therefore, it makes sense to attack individual information in their password. And the cool thing about individual information is that many of those things are publicly available. So if you write a social media harvester script, for instance, you could just scrape the information from Facebook or whatever, if it's publicly available. You could also use website user tables. So for instance, a few years ago, Ashley Madison was hacked, and the password, not only the password, but also the table structure, the database dump, got released on the internet, and you can find a lot of sexual preferences in the tables of this kind of password dump. So there is a lot of information out there. If you are an intelligence agency, for instance, you have a lot of personal information about possible victims. So the basic idea is, this is my approach, you train a neural network with a list, not only containing passwords, but also containing, along with these passwords, information about the person. So use social media information, use e-commerce information, gaming, communication information, all that you get your hands on, and feed it and train it, generate a model, and then use this model to generate a tailored password list to that victim. If you use personal data, there's the GDPR, General Data Protection Regulation by the EU, which basically, if you don't comply, you get a lot of, you have to pay a lot of money, and you basically need consent of your victims in order to process their data. And if we talk about personal information and data leakage, you probably don't have consent to use their password if that's leaked on the internet. Therefore, this is an imbalance. Because as an infosec researcher or a security engineer, you have to comply with the GDPR and probably find less ideal alternatives. And as an attacker, you just ignore the regulation. I mean, whatever, and train it on the best available data. But there are compliant solutions to that. So if you just want to attack general passwords, you only have to train it on the top 10,000, top 100,000 password lists, because they don't contain any personal details. But if you want to use individual information, you have two choices. First of all, there is Article 6 in GDPR, which states that if the processing of data has some public interest, like increasing security maybe, then it would be possible. But please, I'm not a lawyer. Please talk to your lawyer if you want to do that. The other thing is, if you already have user information and you have consent to processes, like if you are Facebook or if you are Microsoft or whatever, then you can use this personal information. The problem again is you need to have the plaintext password, and you need to store that for some time in order to train it. So which means you have to store the plaintext password, which probably isn't the best idea. There's also an alternative. You could extract the information in the password and create a password scheme. So for instance, if someone uses John 1970 exclamation mark, you don't store the password in plain text, you only store first name, year of birth, exclamation mark as the password scheme. But this means that you have to have all the information at hashing time, which is not always the case. So there are a few challenges. First of all, we already have seen that it's possible to generate password sequences, so that's done. But we still have to be GDPR compliant. We have to recognize and relate individual structures to passwords. So, for instance, if you have such a password scheme here, John 1985 exclamation mark and Jane 1992 exclamation mark, it's actually the same password scheme, just with different details here. So you save something like this. But first you have to relate that. You have to recognize that this is a first name. And then you have to deal with obfuscations, because people use like LeetSpeak or something, or like some kinds of obfuscations. So John 1985 in LeetSpeak is a different password than in uppercase or lowercase, but still it contains the same pieces of information, and this has to be considered. So the basic idea is, as a starting point, you use something like exploit-in, because exploit-in not only has the password, it also has the email address of the person. So you have email address and their password. And you use that email address as an identifier, and you enrich it with a lot of information that you can get your hands on, like from a social media harvester. And then you basically get a huge matrix of data, and this could be such a result. So for instance, you have these kind of passwords here, that's, by the way, that's randomly generated. But never mind, these kind of columns here are completely arbitrary. There could be 10,000 columns here. It's completely flexible. The machine would analyze this data set and see, okay, people are using their last name and some integers at the end as a password scheme. Other people don't have any relation to their personal data. Other people use their first name and the second two digits of their year of birth. Others just use their username and so on. And this can be analyzed by a machine. I needed to be GDPR compliant. That's why I didn't use actual password lists. I didn't use actual data, and I made up some fake password creation schemes where I just think of. And one of these schemes, for instance, is just the random scheme, which randomly chooses a top X password list password, like 1, 2, 3, 4, 5, 6. Another scheme would be that the password is easy to type. So like QWERTY or whatever, ASD and so on. Also, a password scheme is to just use the username of the person, or use the first name and exclamation mark, use the lowercase first name and exclamation mark, use the last name and the random integer, use the username in LeetSpeak, use the first name and year of birth 4 digits and 2 digits. So these are the password schemes I used, and they all have a certain distribution in the data set. Then I created a random data set. And we have to talk about tokenization. In the last example here, you see we have a data set, first name, year of birth, and the password is just 1, 2, 3, 4, 5, 6. In this case, there is no personal information involved. So it just learns 1, 2, 3, 4, 5, 6. But in the first example here, we have Max 1983, and that's actually used in the password. So here we have the following structure. We have column first name, column year of birth, and exclamation mark. And here's a very special example here. We have John 86 exclamation mark. And here we don't have the information 86, we just have 1986, and that's something else. And therefore it just recognizes column first name, 8, 6, and exclamation mark. And this is actually wrong, because this is not the part of personal information that we would expect here, but it doesn't recognize this because of exact matching. And there is also obfuscation. I mean, John in normal case is something else than John in LeetSpeak, for instance. So we have to think of these things, how do we deal with that? And the one possible approach is to use on-the-fly word mangling rules in the training phase. So basically you have this kind of data set here, and you basically multiply those columns with different obfuscations. So for instance, you use Tanya in the normal case, then you use it in LeetSpeak, lowercase and uppercase, and you do that for every possible entry there. This blows up the data set, but that's perfectly fine because the machine learning algorithm can deal with that. That's no problem. However, this is just one approach. I spent limited amount of time here. I'm pretty sure fuzzing matching or something like that is possible and will be seen in the future, but this is just one approach. So basically we have solved all the challenges. We are GDPR compliant by using fake rules. We you can recognize and relate individual structures by using the column IDs. We can deal with obfuscations by using the on-the-fly word mangling rules. And then, of course, there's the implementation. I wrote the implementation based on Sean Robertson's PyTorch char-RNN, so I used PyTorch. Here's the GitHub for that, so if you want to play around with that. And I made some adaptions. These are just the main adaptions. I made many more. But basically, it's matrix-based detail matching and on-the-fly word mangling rules. Then you do some training. Training is extremely boring, but you basically watch the screen for half an hour where a progress bar goes from 0 to 100%. But what's interesting, though, is you get results every few epochs. Epoch is just an iteration in the training phase. And at epoch 10, for instance, that's very early in the training process, by the way, you see that the passwords really don't make sense. It's just garbage. Hasn't learned that. But the length of the password is very similar to for instance, the rock queue. Not completely perfect, but still. Epoch 40, you see that it starts to pick up things like common character combinations like ES or CK or EN or ST, but still the words don't make sense. And at epoch 280, it starts to recognize words and but also date structures here before, and so it's like butter or raven or something like that. So you see the progression of the neural network learning these things. And now you can attack the target. You basically create one entry of a new data set, and it has to have the same structure here. So again, this is the structure here. Of course, the password is missing because that's what we want to create. And then you use that, you input that into the model, and you use that to generate a password list. And when you do that the first few times, you see that there's a lot of garbage coming out there. That's not because the algorithm is wrong, but in machine learning, it depends a really lot on selecting the right data set, having the right data set, the perfect data set, and also setting the configuration correctly in the hyperparameter configuration. So let's talk about the results here first, and the qualitative analysis. This is an actual output of this model. Remember, this is not a real-world output, it's just on my fake password schemes here. And what you can see here, all of these schemes that I've mentioned before are seen in this list. So it starts, for instance, with the first name and year of birth 4 digits. That was learned here. Then it's a little weird here. It starts putting out random passwords. That's because it has learned that a lot of people use dates as the password. So it's just probably randomly. Actually, it's not completely random. It's not brute force. It uses a stochastically approximation, so it's better than brute force. And there's some stuff in there. Then it also has some duplicates that would not be seen in a real-world data set because I have only 9 password schemes available, and therefore it's very likely that there is a duplicate in there. But still, it has learned all the other things. In this case, this is very interesting here. First name is, it has learned that there is a first name, but it has not learned that the year of birth is there in 2 digits. Here, we don't have that as a separate column. We could do that. That would optimize the results. But on purpose, did not do that. But still, it got the password. Why? Because it just saw that many of the entries use two-digit integers at the end. And basically, this was approximated. So it did not know that this is the year of birth. It just approximated that there might be some connection between those integers. So now I'd like to prove the scheme adoption. How is that possible? I created a new data set that the machine has not seen before, and I basically separated it. So I created a data set with personal information and a password, and that's multiple times. And I separated that, and then I looped through these entries and generated a 1,000 line password list. 1,000 line password list is nothing. So usually you use like millions of lines for a password list. And then I just checked if I fed this personal information to the model, generated a password list, and checked if the password was on that list. And these are the results. So never mind this one, that's actually just a reference set, but these are different models that I've trained with different configurations, and all of them were able to match around 70% of the passwords, where the rest of the 30% were the random passwords, which would be approximated. So in this case, in order to match more than 70%, you would have to just generate a longer password list. And in this case, it doesn't seem that the configuration of the model really depends on something, but here you can see that it really is necessary to find the right configuration, because some models are able to predict the password way earlier than others. So for instance, the epoch time is very relevant here. And not only matches it the password, it also recreates these password distributions of the schemes, which means that I've basically proven that machine learning and neural networks can learn such information and can be used to attack passwords in that way. So now that's obviously a problem. What can we do about this? First of all, there are several mitigation strategies. First example, what we could do, we could attack it, mitigate it the same way an attacker would attack it. So use the same tool, generate a password list for our users, and check if the password is on that list. You could do that, but the problem is that an attacker uses a different data set. You don't know what the data the attacker has, and therefore it will generate a different model, and therefore it will generate a different password list. So if the password of that user is not on the list you've created, that doesn't mean that there is no list out there created by the same algorithm with different data where it will be on there. So there is another possibility. We could use long and complex passwords, as we have learned. And this is a good idea, and there are several similar strategies. I'm not going to mention them, but basically it has one problem. If you have a password like this, John Smith 1985, you could consider it long enough, probably, but it actually only contains 3 pieces of information. It just contains column first name, column last name, and column year of birth. So it's actually 3 digits of very obvious information. And therefore, a long password isn't necessarily more secure in this kind of attack scenario. So if you really want to make sure that you can't be attacked by this method, you have to treat all human-like passwords as insecure. That's a very radical approach. You could, for instance, warn your users that their password is like 70% human and therefore it could be attacked and so on. You could also implement a password policy disallowing all human passwords. That would be very extreme, but still possible. But the thing is, how can you deal with that? I mean, until now, there is no way of checking or classifying a human likeliness in a password. And I've created exactly that. I created a human password classifier using machine learning and used several classifiers and vectorizers to do that. I'm not going into detail here. I used a data set of 80,000 human, 80,000 machine labeled passwords that looks like this. So this is an example of the data set. You have a random password here with a lot of special characters, for instance, which has the label M for machine generated. Then you have like passwords from a Roku data set, like boxers with H for human generated. And then we have this kind of password and you train it with the model and then you get 99% correctly across all these combinations, so that's really remarkable. So it's in 99% correct. By the way, if someone is interested, that's also the value for recall and F1 score. And this is some kind of output here. So basically, this is a date. So a typical human date, and it says it's 99% human. This is a completely random string. It says 0% human. This is a word here, a human word. It says 97% human. So it's very accurate. It's very good at deciding if something was created by a human or by a machine. But as you can remember, probably, there is also this type of passwords, these human randomly typed passwords. And these are randomly typed passwords by humans, for instance. So these passwords really look like they were machine generated. As a human, I'm not able to tell you that these were generated by a human or by a machine. I can do that. But 83% the model was correct, the already existing model, in these kind of things, scenarios. And then I did a retraining of human random and human machine random passwords, and I got 94% correctly. So that's actually pretty good. Better any human can do that. So let's see a demo first. Don't take my word for granted. So this is my classifier script. I hope you can read it. Can you read it? Yeah. For the password 123456. And guess what? It's human, H. Let's try something else like password. Of course, also human. Let's try something completely different, like I am a human password. Maybe with a 0, something like that, with obfuscations. Human. And now let's try something really random. Here I've written a few lines of JavaScript, some kind of random password generator. Just gonna copy that. It's really a random password. You have to trust me on this. I didn't set up my Wi-Fi, otherwise I could have used something like this. So, and it says machine generated. Actually, in some cases it is wrong, because I've used the default model here, as you can see, the default model. And if this was wrong, that could happen, because I've never tried that password before. In this case, if it would say human, I'd just switch to the human model, which was trained on the human random password, and then it would be right. Almost certainly. Okay, well, conclusion. Machine learning can be used to efficiently attack passwords created by humans. And if you want to mitigate those issues, then you could treat all human passwords as insecure and use machine learning, especially this machine learning implementation, to identify human passwords. And you could use this script to integrate it on your web servers, on your password storage services, and so on. If you want to read my thesis, that's the link. If you want to use my human password classifier, it's available on GitHub since a few days ago. So you'll be the first one to use them, probably. And if you need ready trained models for your production environment, whatever, just write me an email. Okay, so I want to close with a quote of Troy Hunt from haveibeenpawned.com. The only secure password is the one you can't remember. Thank you. Oh, any questions?
Thank you, George. So, okay, he was the first one. So, okay.
Thank you for the presentation. It was very good. From time to time, there are competitions where the guys that are specializing in retrieving the passwords from the hashes databases. Well, during these competitions, usually the guys with the less computational power have the best results. Do you have any knowledge about the usage of such methods during these competitions?
No, I don't have this kind of information, but usually if you really want to crack a lot of passwords, then you need a lot of hashing power, of course, and such neural network calculations are pretty expensive. Therefore, in some cases, it wouldn't make sense to use a neural network for that. My approach here is better used in individual password cracking scenarios. For instance, if you have an online approach, or if you have a limited amount of tries or limited time or something. So if you want to increase the quality of your password list and not just crack all the passwords, that wouldn't be the best.
Yeah, that would be my second question about the efficiency versus hashcat versus this. Okay,
yeah,
that's fine. Thank you.
Hi. Here. I don't know if you have heard about the NIST recommendations from this year, but one of the intriguing recommendation was that users should not be forced to change their password regularly or as regularly as now. What do you think about this? Do you think it's a good, or this question? I think it's about all community, security community. I don't think we agree with this.
Yeah. I mean, password policy is a speech for itself. Of course, if you have such a rigid policy where you just basically allow users to add an integer at the end and just switch the integer to the next integer, and that's the change of the password, of course, that wouldn't be the best approach here. But when it comes to something like this, it's really a usability problem, because if you do that, what I told you could do, like disallowing human passwords, then you probably will frustrate a lot of users. But what you can do with this script as well, I haven't showed you this, but you basically get a percentage of the human likeliness, and you could use this percentage in a form where you input your password and say, okay, it's 97% likely that this password can be guessed or something. Like, you could do that additionally to your entropy estimation, and probably just give them a little background information what you can do with that, and recommend a secure password. But I'm personally, I'm a fan of password managers, so I don't know any of my passwords like the one I used to, you know. Well, yeah, that's my personal opinion on that.
Hi.
Hi.
If you use a machine-generated password, which you can remember, this is the ending quote, how can you safely keep it? Because it might have security policy that prevent you from keeping it in writing, electronic or physical.
Okay, that really depends on your scenario, I would say. Well, if you generate these data, the only sensitive information is the personal information attached to the passwords. If you're talking about generation here, in this case, this would be data that should be saved properly, of course. But the password itself is just an approximation, so you don't really know at this point of generation that this is the actual password. So therefore, well.
No, I mean, how can you safe keep it in order to use it in the future, if you don't remember, if it's machine generated?
Well, the generation is just for the attacker side in this case. So, whatever.
No, I'm using the password, personal password for an application or for the computer.
If you personally want,
Yes. To use a
password manager,
machine-generated password, in order for the hacker not to be able to.
Oh no,
it.
yeah, of course. Machine-generated password would be a better approach if you want to secure it, of course. And if you want to keep it securely, then use some kind of password manager, use some kind of password storage that you trust, of course. Probably don't write it somewhere. But that doesn't really relate to machine learning generation. Thank you. Where's
Hello.
the mic? Hi.
I have it. My question is related to, sorry. So my question is related to if you know the passphrases, the long passphrases used in cryptographic wallets, how vulnerable are they? Because normally they are words like, normal words, but the password is quite long.
Yeah, concerning this approach, they are really secure because they were generated by our machine. They were not generated based on personal preferences. If that would be the case, then it really would be a problem. But in this scenario, it's perfectly valid. I mean, the English language has, please correct me if I'm wrong, has around 30,000 words or something like that. If that's your basis as checking, generating a random password, then that's perfectly fine. I mean, those are like 12 passwords. 12 words, I guess, if I remember correctly. So you have basically 30,000 to the power of 12, which is a lot. I mean, if that's randomly selected, then it should be secure.
Okay, thank you.
So we have another one here.
I've seen that your networking model has successfully generated passwords according to the rules that you used yourself to generate your passwords. But you generated a lot of passwords with those rules. What I'm asking is whether or not it would correctly guess another rule, but that rule should not have as many passwords generated. I mean, if the subset of data is a lot smaller in between data.
The thing is, it's statistically approximated. Therefore, if it is not very significant in the training data set, it won't be very significant in the output, which means in practical usage that you will have to generate a longer password list until such a password scheme is reached. But still, it could do that. It will learn that. But it also depends on your neural network configuration. So if you have a very shallow neural network, then you will not be able to learn a lot of detail about the list. If you have a huge network, then this would be possible, but it takes longer for training. So this is what I meant when I said that you have to choose the right hyperparameters. But it will be possible.
Thank you.
Thanks.
Hi.
Hi.
I want to ask you how you proceed if you have another alphabet, let's say Chinese, Arabic, or other languages.
My script is based on UTF-8, so everything that's in UTF-8 will be covered, but that could be changed instantly. That's no big deal. And I did not choose several characters as a whitelist. I just picked up all the characters that were in the data set.
Yes, but the behavior of any culture will be very different.
Yes, absolutely. And that's why it's necessary to pick the right data set. So if you just want to attack the Chinese market, for instance, then you will have to train the machine on Chinese market data sets. Okay. Otherwise, you won't be very successful. You have seen that in the training slide where it learned a lot of English character combinations. And that's just because I used English passwords as a training source. But
yes, most of them are in Latin.
I'm sorry?
Most of them are in Latin alphabet.
Yeah. So therefore you will have, I mean, there might be some characters in there in the password set if you use a general password set, but the same as with the question before, it won't be very significant because it's just a few lines in there, and it would be a better approach to use most of the password as the scheme you're targeting.
Okay. Thank you.
Thanks.
Hello.
Hi.
There are a lot of studies regarding the patterns of the password, in what position they use the digit, in what position they use the special sign. How do you think your model can help these studies, or do you think that they're appropriate?
Yes, I absolutely think that this is learned by the neural network. I haven't done a thorough research on that especially, but as I watched the output of the model, many of those schemes were present. So, yeah.
Hi.
Hi.
You said that you try to make it GDPR compliant. have you managed to not be able to generate phone numbers or addresses of persons?
Well, I actually used random data here. So there was a random script generating from common US names, first names, last names, and so on. And the other things were just randomly made up. That's just to prove the point. In a real-world situation, of course, you would have to be GDPR compliant and use some information like that.
Okay, but like phone numbers, they could be generated also randomly using your script.
Yeah.
Have you tried to see if they are not being used by some countries in the GDPR based countries?
No, I haven't checked that. I haven't included addresses. I haven't included telephone numbers. I wouldn't check it if it was randomly created.
But in your script, does it check for
No.
specifics?
No.
Oh, I see.
It's just for training. Hi.
Hello. Is there a possibility, for example, I have a password like Mike02 to be, let's say, guest in a brute force, even if it is not my password, a different password to match over, in order to hack into, I don't know, a web page, for example?
What do you mean it's not your password?
For example, my password is Mike01 star. And you generate a lot of passwords.
Yeah.
And is there a possibility that a password which is different from mine to be accepted in order to let someone to authenticate?
Probably, I don't know.
Thank you.
Okay. Are you still available to take questions? We still have like 4
I'm around
minutes,
anyway.
so it's okay?
Yeah, I'm around anyway. So.
Okay, so we have one there. I will.
So in the previous demo you showed us, could you please run the same demo with the phrases, words like staple, correct, horse?
Yeah.
I was wondering what your model would render.
That would
Thank
say
you.
it would be a human password, I'm pretty sure. But actually,
Thanks.
it's a really long password, so we'll see.
Yeah, I assume.
Correct, horse,
Thanks.
battery, staple, human.
Thanks.
Do we have another one?
Okay. Let's see.
Okay.
Yeah, we can play around that like that or like all the time now.
So
It's funny.
we will be taking two more. It's okay.
Okay.
Yeah. So.
Thank you. So about password managers, which one do you think is the best, cloud one or local one?
Well, it doesn't really relate to my talk, but I like to keep stuff at my security level. I don't trust others that much for my passwords. But that's just personal preference. I don't want to offend anyone here.
And do you have a recommendation for a specific one?
I'm not going to tell you the name, but it probably makes sense to be in charge of the source code. So if it's open source, it makes sense for a password manager.
Yeah, that's
it
right.
should be secure, therefore use something like AES 256, whatever, at least. But that really depends on how paranoid you are. But yeah, so open source would be probably a good idea.
Thank you.
You're welcome.
And the last one.
Could you try the generate with a this face roll type password over your keyboard?
What do you mean?
Like randomly typing characters on
The
your
generator?
keyboard. No.
The classifier?
Yeah, that one with just typing.
Oh, I didn't do that. Oh, sorry, that was actually planned in the demo. I completely forgot that. So just typing something here. You have to trust me, I just type anything here. So that's machine generated. That's the example that I told you before. Here it says it's machine generated, but it's actually generated by a human because I just typed it. And now I'm going to try, thank you, by the way. Now I'm going to try the model that's exactly meant for that. And it says human. So that's exactly the point. Because this could have been something machine generated, but you can't trick statistics. it's just not possible, or at least very hard. So in the first model, it says incorrectly M, but if I use the human random model, it says H, so which is correct. Thank you. All right.
Yeah, so I know there are other questions, but you can reach out to George during networking or here. We need to start the other talk. So thank you so much, George. It was so intense. Let's give him some warm applause. Thank you.